and we have delocalized electrons in there. We have to talk about aromats. But before we come to aromats, I think it's time for a break. Let's have 15 minutes break and meet again. If we already sent it to me. No, it won't save it. It marked. You were interested in an internship, not on a bachelor. Yeah, internship. Practical. Yeah. Here. Oh, yeah. Okay. Is it possible for you to come to Rostov each day or 3 days a week? Yes, but I can drop it. There is a train.
Raymond, your microphone is still on.
Okay. Yeah. Complete. Okay, so let's start in the last round for this year. Let's talk about aromats. Even here, I think we already discussed that aromats are hydrocarbons, cyclic hydrocarbons with delocalized pairs of electrons. The smallest aromat we know is benzene. And we have these mesomeric structures. Here we have the double bonds. They can be even on another side. Right? They can be delocalized. So this one jumps over here, this here, this here, then we have them here. Or we say that's similar to write it like this, like that, symbolize the delocalized pairs of electrons in these 6 cyclic hydrocarbon benzene. We have polycyclic aromatic hydrocarbons. The smallest one here is the naphthalene. It is a condensed 2 benzene molecules together, and we have here the delocalized pairs of electrons, and we call it naphthalene. Or anthracene, we call it when we have 3 of them. And this one can be even angular, having 3 of them, but now in an angle. The third one is like this. We call it a pyrene. So here we have different types and a lot of more bigger ones. You just should be able to identify an element. When we have a cyclic system with delocalized pairs of electrons alterning, they must altern. Double, single, double, single, double, single bond. Always when we have it in this alterning structure, then we can move them around, we can delocalize, and then we have an element. It is a planar structure because each carbon is sp2 hybridizated, and the surrounding is trigonal planar. Trigonal because here, of course, we always have a fourth partner. We just don't know it, but of course, in short, is it like we did it? But in real, we have a hydrogen. Additionally, on all positions, we need a fourth partner. One, two, three, the double bond, four. And this is for all the 6 C atoms the case. All of them are sp2 hybridizated. That means it is trigonal surrounding, and the trigonal structure is planar. And if this is the case for all of them, the whole structure is planar. And if this is the case for the condensed one, the whole big systems are planar. Even the graphite is planar. We had the structure just before. The graphite here is a planar. Of course, there could be several layers, only fundamentals between the layers. And that's why we have these layers, which we can use, for example, here in that pen, where graphite is just moved from the pen to the paper, different layers. There is another very interesting topic in organics. We call it optical activity. Optical activity. That's quite important because from time to time, we have the situation that we have a molecule which is created out of atoms and bonds in the same way, but we have 2 different types. And that is what we have with our hands as well. And we have the left hand and the right hand. When you look to the bonds of the bones of these different parts here in the fingers, it's the same like here, but they are not the same. So the binding is the same. Each type, it's the thumb, that's the different fingers, is the same, but they are not the same. And when you look to the structure of molecules, that could happen if you have 4 different partners on 1 carbon atom. Then you can create a molecule which is the one and the mirror picture of that one. Because this is, when I look into the mirror, exactly the left hand looking to me in the mirror. So it is behaving like the original and the mirror picture of it. I'd like to show you an example. The lactic acid. The lactic acid, and it's an organic acid. So we have here the acid group, which is OH and carbonyl on one end. That is the organic acid function. Then we have additionally an alcoholic group, OH, always here it is stand for alcohol, the hydroxide. And then we have the CH3 as the fourth partner. When we look to the carbon atom in the middle, we have 4 different partners. Here we have the carbonyl as the acid function, the carbonyl of the OH here. Here we have pure OH. Here we have hydrogen, and here we have CH3. So this is our carbon, which has 4 different partners. Of course, it's an sp3 hybridization. So that is in the middle of the tetrahedron. At the edge of the tetrahedron, 4 different partners. CH3, OH, H, and COOH. This is what we call, that's the optical center. Well, when we draw it, as already mentioned, this optical center is in the middle of a tetrahedron. That is the carbon I'm looking to. And then we have 4 different partners. We have the COOH, one partner. We have the pure hydrogen, now looking to the back. Then we have the CH3 coming out of my plane of the paper, and in the same plane like the paper, the 4th partner is the OH. That is the same molecule. Now I draw it more likely it is in real. The optical center in the middle of the tetrahedron here, and that is my tetrahedral structure. In the middle, the carbon, and here this one is going back of the plane, and that one symbolized coming out of the plane. And those are in the plane. Lines here symbolize they are in the plane, and one is going back and the other is coming out of it. And it's not easy to draw that in a 2-dimensional plane. And now I try to draw the figure of the mirror. I say, okay, here, that is my mirror. That is the plane of the mirror. And now I draw this one exactly like it would like when I look into the mirror. I have this carbon atom again in the middle of my tetrahedron. That is what I am looking to. Then I have this OH. Now it's looking to the mirror. It's the more likely nearest to the mirror. Here there is no change because it's in the same orientation like the mirror. So C, but okay, OH. This is not a problem. At that side we can rotate. And now this one coming out of the plane, the CH3, and the H is here going back of the plane. Again, we have the tetrahedron. This is our tetrahedral structure. But now I try to draw it as the picture of the mirror of that. And you see it with your imagination. Do you see it? Because here, now we have the OH more here. That is in the same plane that's coming out, and the other one I'm going back. And when I try to symbolize this molecule now in a 2-dimensional form, like I did it here, I press it in 2 dimensions, then it looks like that. When I press the left one in 2 dimensions, then it's like that, because this one comes in the same plane. The hydrogen comes up from the back, and this BH3 is going down to the plane, and that already is in the plane. Now I have it like this. That is what we call Fischer projection. But then we have to know exactly the 3-dimensional structure, and then we press it into one in a 2-dimensional plane. And when the OH is on the right side of the disk process, we call it D. D for dexter in Spanish, derecho. Dexter in Latin is the right side. So D, lactic acid. D symbolizing that we have these alcohol group on the right side in the 2-dimensional writing. When we do it here now and we press it in 2 dimensions, let's try it. Here we have the optical center, or carbon, and now we press this one in the 2-dimensional form, then the OH is on the left side, the hydrogen is on the right side, and to the acid group, nothing changes. And here, that is in the same plane. What you see now, here now we have the OH on the left side. That's why this one is called the L. L, left side, lactic acid. And those 2 molecules behave like the original form, and it's mirror figure. They are not the same. By rotating all these sp3 bonds, we are allowed to rotate all of them, but we never come from that one to that one. Maybe it's a little bit difficult to imagine, but believe me, in every case, when we have 4 different partners in pure sp3 hybridization, we have an optical center. And then we have 2 forms of that molecule. I think I already talked about in chemistry, mostly, this is not a big problem. The chemical behavior of those molecules is the same. But in biology, it's not the same. In biology, enzymes can distinguish between the L and the D type. Because we have always enzymes, they are working when they are in contact with some molecules which are needed for some biological reactions. They are working like the key and the lock. And they fit together, and then it works. But when this one is turned around, it doesn't fit. So in this case, some biological systems, D and L form makes a big difference. The one can be used, the other one not. If you look to your yogurt, to some maybe other food, sometimes you can read on it, this yogurt has a high content of D milky acid, for example. And some people say, okay, the D version is more healthy than the L, or we can use it, and the other one not. We have another example, 50 years ago, the contingent children, maybe you heard about. And they have some misbeliefs. The mothers, when they were pregnant, they took they couldn't sleep, and they took a drug for sleep, better sleeping. And at that time, they didn't know that there is a difference between D and L of that molecule which helps to sleep. And the one wasn't the problem, the other one was the problem, because then the children in the body of the mother were misbuilt, and continent children were born. Since that time, in the production of pharmaceuticals, the industry has to check both D and L version if there is any negative follow-up of the one or the other version. That's just that you have heard it in biology. It's a big topic to divide, to distinguish between the two options. In chemistry, mainly not, because chemical reactions don't divide between the different forms. Then let's talk about systematics in organic chemistry. Or let's name the nomenclature. Aliphates, that is the first group. Well, what do you already know about aliphates? Aliphates is totally linear or angular carbon lines, sometimes with heteroatoms. So linear hydrocarbons. Or angular hydrocarbons, sometimes with heteroatoms. Heteroatoms. Do you know what heteroatoms mean? Not carbon and not hydrogen. Hydrocarbons are carbon and hydrogen, and sometimes they have even others. A pure hydrocarbon is, for example, propane. Well, this is CH3, CH2, CH3. If we talk about the aliphates, the first one we know, the smallest one, what's the name of it? Pure hydrocarbon, only one carbon atom, methane. Methane. That's CH4. The second one, two C atoms, only ethane. And CH3, CH3. Then we have the propane, and when we now prolong it to the butane, then we have at the end always CH3. In the middle we have CH2, CH2, and again CH3. Now you see, when we just have linear structure, we just add a CH2 in the middle. Then we come to the pentane. Pentane just has more now. Pentane, CH3, CH2, now 3 times CH3. Pentane means in total 5. 1, 2, 3, 4, 5. And ongoing, hexane, heptane, octane, nonane, decane. This is pure aliphates without any double or triple bond. Only sp3 hybridization. We can even have another one. Let's have a molecule like this, CH3. Then we have CH3. Now we see we have an angular, because now we go on with CH, and here a double bond and CH3 again. Now, do you already know how to name this molecule? We have 1, 2, 3, 4, 5. So it is a kind of pentane. Yeah, or yeah, we have to count from the right side here, because we always start counting the carbon from the first irregular situation. Here the irregular situation is the double bond. Yeah, let's check it. So you say 3 methyl, yeah, and then 1 butane, because the one is important because to talk about where do we have the double bond.
Just for the last carbon on the right, shouldn't it be H2 instead of H3?
You are totally right. Yeah. Thank you. Very good, huh? So that was not my aim, but it is a good check if you are aware. So the name is, now we call 3, and here we have the methyl group, 3 methyl. And then we say we have butene as the drain, 4 of them in the main structure, but we have a double bond on the first carbon. So we have 1 butene. So aliphates always end with A when they have no double bond. So no double or no triple bond. Then the ending is A. We have to count the number of carbons, and then it is an A. So propane, butane, pentane, methane, ethane.
The one that you wrote 3 on butene is not an aliphatic, right?
It's not what?
It's not an aliphatic.
It's an aliphate because it is only containing carbon and hydrogen. Sorry, it has?
It doesn't have one, right?
The double bond, yeah?
That's how.
The number of bonds is not talking about if it is an aliphate or not. Just the type of the bondings.
The sentence that you wrote at the bottom is the definition of aliphate, right?
Here.
Yeah.
Linear or angular hydrocarbons. Sometimes with heteroatoms. No double, no triple bond, then we have A.
Okay, this is just a random sentence.
That's only the aim of the ending of the number, propane. Other aliphates have one, when we have a double bond, 1, 2, 3, maybe even more, then just the ending of these aliphates, then it is -ene. Butene. It's not a butane in this case, it's about butene because we have one double. And we have minimum one triple. Then the ending is -ein. That's just dealing with the ending. If you have,
Raimund,
ja,
es gibt einen schwarzen Schatten über deinem Skript, der es zum teilweise unleserlich macht. Er ist immer noch da. Ist die Lampe eingeschaltet vom.
ja, die ist an. Jetzt weiß ich nicht, wo der Schatten hinkommt. Exakt.
Vielleicht die Justierung von der Lampe. Jetzt ist es ja, viel besser. Ja, danke.
Okay, so this ending is only related to, do we have a double bond or triple bond or no? Well, let's talk about some examples. Let's talk about ethane. Ethane. We do not have any double or triple bond, only single. So this is CH3, CH3. Only sp3. No double, no triple bond. Ethene. Now, here we have a double bond. So we have only here CH2, now the double, and CH2.
Only sp2.
So we have here sp and sp2. The single bond is sp3, sorry, sp3, and the double is sp2. But here we have an sp2 additionally. And ethine, then we have a triple bond, which leads to a linear structure, 2, 3, because now we have here an sp hybridization. And the difference is the ending. Ethane, no double, no triple. Ethene, we have a double. Ethine, we have a triple. But all of them are aliphates. Yeah. Now, let's talk about another one. Let's talk about propane. Yeah, then it's easy. It is a CH3, CH2, CH3. Let's talk about another one. Let's talk about a butane. Now, it might be problematic because we are not knowing where to place the double bond. We have two different options. We can say it is at the end. Then we have here CH2 double bond, CH, CH2, CH3. Then we count it from the 1, 2, 3, 4. This one is the 1-butene. Or even but1-ene. But we have a different one. It can be C, and now the double bond, C, CH3. Then we have here CH3, we have here H and H. Again, the sum of it is 1, 2, 3, 4, C4, 1, 2, 3, 5, 8, H8. Again, here's C4, 3, 4, 5, 8, H8. Even here, but now the placing of the double bond is on position 2. So it's a 2-butene.
We can write bu2 or we can write 2-butenes.
Yeah. Maybe if it is getting more complicated, you have to add more different things, then write it at the end. It is but1-ene. This is but2-ene. In this case, it's not a difference, but it could be a difference. I will give you an example. Let's talk about, we already had an example, but let's talk about a molecule like this. We have CH3, then we have a double, no double, we have now a double bond to the next one. Then we have a single bond. Then we have here CH3, and we have here a C, H, and again a double bond, and H, H. Here we have an H, and here we have an H. Now, help me. What's the name of this molecule? Let's now count from the first position here on the right. That's 1, 2, 3, 4, 5, 6. Now we have 6 in the line, and we have 1 angle. What will be the name of this molecule?
3,5x1,4-ene.
Let's have.
3,5x1.
We have not 1-ene, we have 2-ene. We have a diene. 1,4-diene. So we have 1, 2, 3 metal, 1, 4-diene, but what is the name? Hexadiene. So we have a 3 metal, 1, 4 hexadiene. Di means 2 of them. And 1, 4 means the position of the double bond. So it can be quite a long name, but the systematic is always the same. There are even cyclic aliphates are existing. Well, let's have a structure like this. We have here, that is always a cardinal at the angle. But now we don't draw the benzene molecule. We have here at all points an sp3 hybridization. There is no double bond in that case. We all have most of the carbons, which is just here in the crossline. Carbon. 1, 2, 3, 4. That's all the cross points. The name is 1, 2, 3, 4, 5, 6. Cyclohexane. Cyclohexane. It's a pure aliphatic, but cyclic. No double, no triple bond. The difference could be the N-hexane. The N stands for, that is the linear one. This is CH3, CH2, 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 CH3. 1, 2, 3, 4, 5, 6. In every case, the sum of the formula is C6 and 6 times H, H12. Here and here it is 1, 2, 6, C6, but now we have the linear one, 3, 5, 7, 9, 11, 14. Both are hexane, but the one is linear, the other one is cyclic. Due to the fact that we have a cycle, there is one partner more the carbon, not the hydrogen, on two sides. So on those two sides, the partner is again a carbon and not an additional hydrogen. So 2 hydrogen atoms missing in the cyclic form. When we come to the aromatics, then we know the aromate is here. The formula is C6H6. That's benzene. Because here we have double bonds. So each carbon 1 hydrogen less. This is C6H6. This is an aromate, not an aliphatic. Aromat. That's not an aliphatic. It's an aromat, the benzene. When we have heteroatoms, as mentioned before, let's talk about, let's say, the 1, 2 dichloroethane. The 1, 2 dichloroethane. Please help me to draw the structure of this molecule. It is an aliphatic, no double bond, A, and 1, 2 dichloro. What do you think does it mean? So we have here C, we have Cl and HH, and C, Cl, H, and H. The 1 and 2 dichloroethane. It doesn't make any difference if I draw it on the top or on the bottom, because each of these bonds can be rotated. There is no double. I'd like to show you another one. 1, 2 dichloroethene. Now, think about it. Here, there are 2 options. Cis trans, very good. Let's talk about the cis 1, 2. The cis one looks like now we have a double bond. The double bond, remember, fixes the rotation. We can't rotate. So this is a difference if we have those 2 chloroatoms, heteroatoms. on the same side, this is the cis one, and the trans, now we have it in the opposite side. Here we have it on the top, and here we have it on the bottom. So these are two different molecules because we can't rotate on this one because we have a one which fixes the rotation. If you remember these overlapping p orbitals here, if we rotate them, the bond will be cracked. So there is no rotation. These are two different molecules. Here we don't only have one, here we have two. Yeah, the 1,2-dichloroethene. Or ethine. Here, of course, there is only one, because there is no other atom. We have a triple bond. It's linear. There is only one object. The normal linear sugar molecule, I will draw it because this is what we might have to discuss about in renewals later on when we talk about biomass. The photosynthesis, we already know, the photosynthetic reaction, just to remember, CO2 plus water leads to C6H12O6 plus oxygen. And to balance, we need 6, 6, and 6. And this is the glucose. Or later on, we just say that is our typical biomass molecule. And we have a linear structure and a cyclic structure of this molecule. The linear structure I like to draw is the C6, C, 1, 2, 3, 4, 5, 6. C6, and then we have here the other atoms fixed to the carbon. We have an OH here, so that is a polyalcohol. And then we have here, we have here, we have, for example, here, and we have here, and here, and again here. This is, if you look to it, we have an optical center in this molecule, or even more. Yes. We have 6 carbons. Yes. Yes, we have. Yes, we have. Now, for example, here we have this is one, this is one, this is one, and this is one. So we have 4 different partners. So here we have an optical center. Even here, but even here, there are a few different optical centers. So even here, this is a Fischer projection, and I learned it when I was in school to say we have it. We don't care about the first one because this can be rotated. Even here, this one can be rotated. Then when I rotate it, the OH comes to the left side. When I rotate it, the OH comes to the left. But the second one here, Ta-tu, ta-ta. Ta-tu, ta-ta. When I have ta-tu, ta-ta in this one is the D glucose. When this is on the right side. Just to here, when this one in the Fischer projection is on the right side, it's the D glucose. But that is more sophisticated to imagine the 3-dimensional structure of this molecule and then to express it in a two-dimensional form, and then to see that this OH is on the right side, and then we have the difference. Because this is an optical center as well, just one of them.
Professor, optical center and a chiral carbon, same thing.
Again, an optical center and
Optical center and a chiral carbon, are they the same thing?
a chiral.
Chiral, like all the four groups. Yeah, all the four groups, they're separate. They're different. For example, the carbon that you mark with the star is connected to an OH by itself. Then it's connected to the one that you marked with the star.
Yeah.
Yeah, it's connected to an H. Different, OH, different. Then it's connected to CH2OH, which is different. Then it's connected to C4, whatever.
This is different. This one.
Yeah.
We have 4 different types.
So an optic center needs to have 4 different groups.
4 different groups. What was the name you were talking about?
Chiral carbon. Chiral, C-H-I-R-A-L, chiral carbon.
C-H, chiral.
Chiral.
Okay, chiral. Yeah, it's a chiral. Chiral, it takes from the German chiral center.
Yeah.
Yeah, that's it. That's the second. An optical center, chiral center, or we call them chiral. Those the molecules, if you have 2 different types. Yeah, I didn't understand it. Okay. So this molecule can be rearranged in a cyclic form. Cyclization. And the cyclic form is now here, looking similar to this one. One of the oxygen atoms is integrated into the cycle, and the other ones are used. When we use one O in the cycle, the CH2OH looks out of the cycle. And each of them having a H and a OH. It is not an aromat, it is an aliphat. And this is, at the end, the cyclic form of the glucose. And when we go further, there is even a difference in this one. When we create the cycle, the OH can look above the cycle or below the cycle. And this is what we call alpha and beta glucose. Maybe you heard about it. And then this glucose, that is a monomer where polymers can be created in nature. And we know those polymers, formation of polymers, we just interconnect those cycles to long structures. I think you know them. One of these is starch. Starch is a polymeric molecule where this is the monomer, and a lot of them are connected to long chain, and that's starch. We have it, we eat it every day in bread, in whatever, in noodles, in a lot of things. Okay? So that's starch. The other one is very similar, but we don't eat it. It's cellulosic. We don't eat it. We can't eat it. The difference is only related to if this OH looks up or down and how it is interconnected. Are those connected like this or like this to the long chain? When they are connected like this, it's at the end, it's going always in the same direction. And then you have a helical structure of this linear polymer, that's starch. If you alternate each time, it's getting a fiber structure, the cellulosic fiber. The starch, we can eat it because you just can try, take bread in your mouth for a while and it's getting sweet. Then these polymer is cracked into the monomers in those, and that's the sugar, the sweet sugar. Because we have enzymes in our mouth which are able to split starch into the monomers. Starch is two different starch molecules. One are really linear, one have a side line. They are called amylose and amylopectin. And the amylase is the enzyme splitting starch into the monomer. For cellulose, we don't have that enzyme in our body, even in our environment, not easy to find. So we can't eat it. We can take a piece of straw in our mouth and for hours, it won't get sweet. And if we eat it, we're not able to digest it. For the starch, we can. So a big difference. How it is interconnected. One is our main food, the other one we can't eat. Of course, there is some enzymes even for splitting cellulosic materials into the monomers, but they are not very ubiquitarians. We find them in the rainforests, for example, because in the rainforests the compost, the compost to make compost, to convert the biomaterials at the end in CO2 and water, the decomposition that works quite quick in the rainforests. Not typically here, but in rainforests, and there are enzymes splitting even cellulosic materials, but not very ubiquitarian in nature, so we are not able to eat it.
Professor, are fructose and sucrose also pointers of?
Yeah, these are just fructose. We have a lot of different size of the polymers. We have two of them in saccharose, and 3 and 4 being like oligo saccharides. And then we have polysaccharides, and the polysaccharides is the starch, and the different one have different names. Okay. In the aromats, we even have some things. I think it's 44 now. Aromats with heteroatoms or heterogroups. There is one very important molecule. Here we have the benzene, but now instead of a hydrogen, we have an alcohol, OH. The name of this is phenol. That's the functional group here. And this is an alcohol group. So, well, the OH always is symbolizing it is an alcohol group. And this phenol is the base structure of lignin. When we talk about wood, it is a lignocellulosic material. One part is lignin, and the other one is the cellulose. And lignin is created out of a phenolic base structure. It is not as simple as cellulosic material. It's not having always the same monomer. Lignin is much more complicated.
No.
This one, functional group, alcohol group. Lignin, phenolic base structure. So the wood ligno I'm not able to write anymore. Lignocellulosic material. That's a mixture of lignin and cellulose. The lignin is mere plastic structure, so it's giving the pressure stability to the wood, and the cellulose is giving the when I try to stretch it, the stability in this direction. So I always compare it like it is a Weber-forced polymer. Wood is a Weber-forced polymer. The lignin is the polymer base structure, and the cellulosics in there are the fibers. So in nature, in engineering technologies, we create some polymers with a high stability. We put in fibers. The celluloses, this long chain, are in the wood in all directions. They are really very strong, giving this stability in elongation. And the lignin, I can't press it. In combination, it's a very stable material. Okay. So we already talked about the alkanes, the alkenes, and the alkynes. Then let's talk about hydrocarbon derivatives. What was the last number? 6566 now. Hydrocarbon derivatives. Even here we started to talk about derivatives, it's not the halogen hydrocarbons. Yeah. Look to the 1,2-dichloro, for example. Thing. And we had some others. These are the halogen. The alcohol is another derivative of hydrocarbon molecules, alcohols. The functional group is the OH. That's the alcoholic group. Ethanol. O always symbolizing we are talking about an alcohol. So here we have CH3, CH2, OH. Oh, even here we have to talk about where we do have the alcohol function. When we talk about 1-propanol, then the alcoholic function is on the first C atom. That's the first one. 1, 2, 1-propanol, symbolizing here on the 1 position, we have the alcoholic function. When we talk about the 2-propanol, then we have the alcohol function on the second one, CH, OH, CH3. And then we have 1, 2, 3. Now we have the alcohol function on the second carbon atom, but only because it's an alcohol. In both cases, C3, H3, 5, and 3 or 7, H7, OH. It's in both cases. 1, 2, 3, 3, 4, 7, OH. So the sum formula for both is the same, but the structure is different. We even can have 2 alcohol or 3 alcohol function in that. For example, the 1, 2, 3 propane 3O. If we have to draw this one, this is the C1, 2, 3, and OH on the first, on the second, and on the third. And then we have here only hydrogen as additional partners in the bonding. Everything is sp3, and we have the 1, 2, 3, 1, 2, 3, propane, trio. 3 alcohol functions on the position 1, 2, 3. This is an important molecule. It has a name, another name, short one. This is glycerin. Glycerin. And even this is what we will need in course, because that is one part of the main structure of plant oils, like sunflower oil or rape oil or others, palm oil. All of these oils are created out of glycerin and fatty acids. An alcohol and fatty acid can convert it to an ether and water. We will talk about this. Fatty acids are another point. Fatty acids is a special form of carbonic acid, of carbox. How do you call it? Not carbonic, carboxylic acid. Sorry, the English carboxylic acids. They are very long chain. So we have a lot of essential fatty acids, which we need. Those who are vegetarian, is there one here who is a vegetarian or vegan? So you might have heard about some important fatty acids. If you